Hello, welcome to session number 15 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam. Today I'm going to take a filter which we realized earlier and I'm going to implement that filter in a LTCC process. Right, so again, the distinction between you as a designer and application engineer is, for example, a filter is a broadside coupling filter like the one shown in the figure here. Okay, what he will do is he will put in these lines with certain arbitrary widths and certain arbitrary spacings, and then he will put a goal on S11, S22 and S21 and then try to run an optimizer. Well, that's a blind way of designing a filter and doesn't give you an idea how to implement the filter, because you do not have an idea of what is uh, what is the structure of the filter and how it works or why it works, right? So you have to be a designer, you don't have to be an application engineer. So let me go ahead and show you a design of a bandpass filter from a circuit level. So if you remember, we implemented a filter of this form. In this form there is a, LC circuit which is an anti-resonance circuit, and then there is a again LC circuit which is a series resonance circuit. So now there are two resonances. Okay, now one is an anti-resonance circuit and the other is a series resonance circuit. Now it's difficult to implement two different resonances on a substrate. So what people do is they implement only one of the resonances. For example, they can implement either just the series, and then they would have what you call a impedance inverter. So the basic structure would be, uh, let's say, let me just draw a little. Okay, so the basic structure would be, uh, just 1 second, bear with me for a second. Okay, I'll show you. Okay, so the basic structure would be some form of a, let me just do it quickly so that, okay, so let's say this is the inductor. uh, okay, so now we have a what you call a resonator, right? So there is a series resonance and there is a shunt resonance. So let's have a series resonance which is a series L and series C, right? Okay, just 1 second. So what we have here is a going to have a capacitor, right? Okay, so this represents a series resonance. Now if you try to implement a lump component, sorry, if you try to implement a lump component based design, then you would have problem with the parasitics, right? So uh, the problem with the parasitics, right, is that they are they are unknown, they are not predictable, and when you put two or three of these components together, they start interacting with each other and they couple with each other, and all your filter response is spoiled, right? So basically, okay, so let's have a resonator like this, right? So this is a series resonance, correct? And then there's going to be shunt resonance. So the basic structure is that. Now if we were to implement this filter using these series resonance, and in between I am going to put what is called impedance inverter Z inverse. Okay, so a quarter wave line is an example of an impedance inverter, right? As we have seen in the previous sections, right? Quarter wave line is a impedance inverter. Okay, so we can use this, what I represent as Z. Okay, so let me insert a text box. Z. Okay, so we can implement this kind of filter. right? So we implement only the series resonator, and whenever you require a tank circuit, we have some form of a impedance inverter, right? Now this can take a form of this form. So this impedance inverter can just be a transmission line. So there are three options you have. Okay, you can have impedance inverter as, so you can use a, sorry, you can use a quarter wave line, and this is what we do in quarter wave filters, right? And then you can also use a shunt capacitor. For this you can use a shunt capacitor. That means that you are going to use some form of a discontinuity, okay? Or you can use a shunt inductor, which will give you a impedance inversion. Now there are three components like this, right? So this bandpass filter, which looks like this, I can take the series elements, represent them as resonators, and the resonators can be just a uh, lambda by 2 line, right? A lambda by 2 line can act as a resonator, right? And then you can have the impedance inverters in between, which can be some form of a discontinuity, which may be a edge coupling. For example, this can be as simple as a line, right, of a certain impedance, and then you can have a coupling between them, right? So you can have these lambda by 2 lines which are acting as resonators, but then you can have a coupling between them of some form, right? Now this structure can be used to implement this. Another way to implement this would be, i I can implement the shunt portion of it, right? And the way to implement the shunt portion, just one second, sorry, bear with me. Okay, this is in between some time I'm taking so that you can understand what I'm trying to do, right? So this will help you also, so don't worry about the time I'm taking for now. Okay, so what I have is a capacitor in parallel with the inductor, correct? And just one second. Okay, so you can have this combination, insert shape, just one second. Okay, so this is a shunt circuit, correct? This is the anti-resonance circuit here. Sorry, bear with me a minute. Okay, group. Okay, so I can also represent the same bandpass filter using these resonators, and these resonators are separated by a admittance inverter. So this is a parallel version of it, right? So I can have uh, J. I can have J in between. So J. Okay, so the idea is to design this filter using only one resonator and then using an impedance inverter in between, right? And this impedance inverter can be as simple as, again, a quarter wave line, a series inductor, or a series capacitor. Okay, series capacitor or a series inductor, right? So I can implement this parallel version of it, right? Or I can implement the series version of it. Now it all depends on what kind of capacitance do you require. So for example, the coupling can be this form of coupling, which is edge coupling. but it can also be a coupling which is a broadside coupling like this, for example, right? You can couple them like this, right? Okay, so this is called a broadside coupling. Again, this overlap length, sorry, this overall length is going to be lambda by 2, but then this overlap length is going to be lambda by 4, right? So, and then there can be coupling between them. So what do we have? We have something called the width of the line and the spacing, right? These are the basic things. So spacing will decide basically the capacitance, right? And that capacitance would be the J, right? So this spacing which brings the coupling is that J, right? And then you can implement a resonator using a lambda by 2 line, right? So this is how you can also implement a filter. So now let's very quickly see what is the maths which goes into designing this impedance inverter J, because the resonator is very simple. It's lambda by what you call lambda by 2, and then the overlap is lambda by 4. So this is very simple. But then what should be the width? So basically that will decide what is the impedance of the line. And second, what is the spacing? So that will decide what is the impedance or admittance inverter, right? So again, I usually go to the books, and you can go to Mathai, Young and Jones. Let me look at this. Okay, so now it says that once we know the fractional bandwidth, that fractional bandwidth is basically omega 2 minus omega 1 divided by omega 0, where omega, just one second, okay, over here, omega 0 is omega 1 plus omega 2 by 2, and omega fractional bandwidth is omega 2 minus omega 1 by omega 0. So my filter is between omega 1 and omega 2, right? And then the center frequency is omega 1 plus omega 2 by 2. So once we have that, right, now we have to find out the order of the filter. Now I am going to go, so this will basically go to the table. It will find out the omega by omega c minus 1, and then establish the order of the filter depending on the attenuation you are looking for. But what I have done is what I have shown earlier, right? So this is a Chebyshev filter, as you can see. This is for a certain ripple, which is 0.1 dB ripple, and then I am desiring minus 40 dB at let's say minus 40 dB. I'm desiring it at, let's say, twice the frequency or something like that, right? Now if I play with the order of the filter here, okay, 5 will not meet it, right, and 6 will meet it, right? So I'm going to decide that I'm going to use a 6th order filter. Now for that I have written a MATLAB routine. Okay, that MATLAB routine was here, which gives me the normalized filter components, right? So I can say that I want filter components which are this. Okay, so here this is 0.1, and this is 6, order 6. So these are my filter components, right? G1, G2, G3, G4, G5, G6, and G7, or Gn plus 1. So G0 to Gn plus 1, these are my filter what you call normalized components, right? So once you have that, okay, you go to this particular book which talks about how to go about designing this. So this is over here. It says that these impedance inverters normalize to admittance Z0 or Y0, which is 1 over Z0. J01 by Y01 is square root of pi delta, okay, pi delta twice of G0 G1. So your G0 G1 is over here, right? Your normalized components, right? Or you can get it from the table or the algorithm. And then G, J and J plus 1, Y0, normalized to Y0, for J varying from 1 to n minus 1 is given by pi fractional bandwidth divided by twice of omega 1 dash, which is 1, divided by square root of gj and gj plus 1, and up to the last component you will go, and the last component, the g0 is 1, right? And Gn plus 1 is 1. So these two values are going to be the same. Okay, so J01 by Y0 is going to be same as Jn plus 1 by Y0. So once you do that, you can find out what are the even mode odd mode impedances. So now the way to analyze this is the following. Now this is a coupled line. So when we designed a 10 dB coupler, if you remember in the previous section, we designed the spacing and the width of the line. So what did we do? We found out using that coupling coefficient, we found out Z0E and Z0O, that is even mode odd mode impedances, and from there we establish the width of the line and the spacing. Same thing we are going to do over here, right? So what we are going to do, we are going to establish for every going from G0 to G1, there is a segment which is going to be lambda by 2 with a certain width, right? And then a certain spacing with the next element. So the ZOE and ZOO you determine by this formula. Once you have ZOE and ZOO, you plug in the same formula which you use for coupler, right? And then you find out the width and the spacing. So for that, I have written a MATLAB routine again here, where I feed in the ripple, the order of the filter, Z0 which is 50 ohm, F2, F1 basically is the corner frequency is 9 and 11 gigahertz, epsilon r is 5.92, and h in micrometer, I'm going to use 4 layers, so 97 into 4, right? So that's what I'm going to use, 97 microns multiplied by 4, and thickness of the bottom is included, so the substrate is going to reduce by 9 micron. So 379 micron is my height of the substrate. So if I plug that in, so I have that in here. Okay, so what do I have? I have 0.1 as a ripple, then 6 is the order, 50 ohm is the impedance, and then F2 is 11 gigahertz, F1 is 9 gigahertz, then epsilon r is 5.92, and what you call the height of the substrate is 379. So once I do that and press enter, I have the widths of various sections. So if I say W underscore micrometer, so these are the various widths of the lines, and the lines are going to be of a length which is lambda by 4, and 2 lambda by 4s are clubbed together to make a lambda by 2. So lambda by 4 line would be that. So this is going to be 3.486, okay, or you can say 3486 microns. Okay, so this is that, and then the spacing. Okay, so the spacing would be, the spacing between the lines will be 15 micron, 15.2, 72. So each section is differing by different spacing. So let's lay out this filter in ADS. Okay, so I'm going to go here, and so the response I'm planning to get is this Chebyshev with the 6th order filter with at least 40 dB isolation and the ripple of 0.1 dB. Now this is the ideal Chebyshev polynomial, right? And you are seeing the ripple, but then there are two losses in it. Okay, the two losses are the conductor losses and the dielectric losses. So if there is a dielectric, right, in this case is a borosilicate with a 10 delta of 0.0023, right, and then there is a conductor of certain width, there are going to be losses per section, and as many sections are there, that much losses would be there. So this whole ripple which you see here as 0.1 dB would be L insertion plus 0.1 dB ripple. So that will be the total insertion loss which you will see in this filter. So this is different from the ideal filter. In ideal filter, you could do it without a, for example, over here, I didn't insert any losses here, right? None of the components were lossy. But now when we are implementing it practically on a substrate with a certain loss or 10 delta, you are going to see all that insertion loss come into our pass band. Okay, so let's go ahead and lay out that filter. So we have to have these sections. One more thing you need to know is the end connections are 50 ohm lines. So I am going to run a line cal. Layout tools, let's run a line cal. Okay, and I want to know a 50 ohm line on that substrate at 10 gigahertz, right? So the substrate epsilon r is 5.92, right? And then height of the substrate is 379 micrometer, and the thickness of the metal is 9 micrometer. Okay, conductivity is 5.86, which is basically 5.6 here. 5.86 is roughly copper, and then 10 delta is 002, right? And I want just a 50 ohm line for the end connection, for the edge connection to the SMA connectors, so that the pin rests on it. So I want a 30-degree, let's say 30-degree line. Okay, and I want the results in micrometer. So I'm making a 50 ohm line for just the end connections and say synthesize. So I'm looking at 566 and 1205. Okay, 1205 and 566. So let's lay it out. Go to ADS and go to new layout and call it BPF lay. Okay, so this is BPF lay. Now let me see if I'm recording, because sometimes I'm speaking to myself. So I'm recording. Fine. So create the layout. Now in this layout, first a 50 ohm line. So I will insert a coordinate entry as 00 as absolute, and then relative. Then this is going to be 566 and 1205. 1205 and 566 and say okay. Okay, we did a mistake. Well, we will correct it. This is on M7. So let me tell you what we are doing here. Let me open a substrate. Okay, so this is our 8-layer LTCC substrate. I'm having a structure on M7, while I'll take the 4 times of the height, so of 97. So 1, 2, 3, 4. So M3 is my ground plane and M7 is my structure, right? So once I have done that, let me change this to M7. The next section is going to be the width of the line, or the length of the line. So let's look at the length of the line. LEN micrometer. It is 3486 or 3487. Okay, so 3487. Insert coordinate entry 3487, right? And then the thickness of the line, right? So, or the width of the line. So width of the line is 343.97. So 344 is the width. 344 is the width, correct? And say apply. Okay, so it is wrong way, so it doesn't matter. I am going to just match this corner here. Okay, so this is done and it is going to repeat. So I am going to take this and repeat it over here. And the spacing, the first spacing which you have is 15.27 or 15.3. So let's put here 15.3. So add it, move relative 15.3. 15.3. Okay, so this is the spacing. So this is a very teeny tiny spacing here, right? Now the next thing is I want another line which is going to be again the length of the line is 3487 and the width of the line is 554. 3487 554. Insert coordinate entry 3487 and 554. Okay, and hit OK. So that is going to be the next section, and this section I'm going to repeat with a certain spacing, right? So let's do the spacing now. The spacing is, next spacing is 72.6. 72.6 is the spacing. Okay, edit, move, relative, 72.6. 72.6 is the spacing. Okay, so once this is done, what's the next line? The next line is going to be insert coordinate entry 3487 is the length of the line, and the width of the line is 616.3. 616.3. 616.3. Okay, so now this doesn't make sense. Let me just check it. What is the width of this line? 2847. So we did a mistake, right? Uh, this line should be the same as this line length, right? So just bear with me. Let me make this correction that this has come up. So these lines should be the same length. Okay. So I was going to do a mistake. Anyways, so the next one is over here, which is the same. This is going to be 6 width of 616.3, right? And then this is going to repeat. Okay, and the gap is 123.3. Okay, 123.3. So let me go back. 123.3. Edit, move, relative. 123.3. Okay, so now let me just make sure this is correct. This is 72 point something. This is 123.3 and this is 15 point something. Right? Okay, fine. So once we are done with this, right, then there is going to be another element here, right? So that element is going to be, let's see, what's the next element? 624.8. 624.8 is the width, right? 624.8. So let's do that. 624.8. Insert coordinate entry 3487 624.8. Let's verify this. 624.8, right? 624.8, and say apply. So there will be a teeny tiny gap, right? This is the width difference, doesn't matter. So now this is half of the filter is ready, and if you see, the other half is a repetition. If you see, 624, 616 is a repetition again here, then 553 is a repetition here, and 343 is a repetition here, right? 343.97. Let me see the width measure. This should be 343.97. 344, correct. Okay, so this is half of the filter. So I'm going to combine these sections. Okay, so this is the first section. So edit, merge union. Then this is the second section. Edit, merge union. And this is the third section. Edit, merge union. And this is the fourth section. Now this is a first cut design, so I'm not sure how close it will be. Edit, merge union. So we have done that. Now I want to tell you that as in case of antenna, there is a certain width, right? And then for that width there is a fringing capacitance, right? So this fringing capacitance causes the length to look bigger, right? So everywhere, so this length is lambda by 4, right? Right? So these are all lambda by 4 lengths, right? And this whole thing is lambda by 2. So anyways, so this overlap has to be, or this length has to be reduced. Let's reduce it by, so it's usually 0.1 times of the height. So the height of the substrate is 379, so 37.9 or 38. So I'm going to move this in by, let's say, 30. So edit, move, relative. So I'm going to make it minus 30 micron. Right, and then this one I'm going to make plus 30. Right, again this one is going to be minus 30. So I'm reducing the length of the line because of the fringing or the end capacitance. So this I'll cause plus 30. Right, very minute differences are there, right? Again this line is coupled over here, so I will cause this as 30 and this one as minus 30. Okay, so basically you can see this gap is going to be minus 30 on X, right? Okay, so this is done, half of the filter. Now I'm going to take this whole thing, make a copy of it, rotate it out, and place it somewhere here. Uh, this one aligns with this one, and then create a gap. And what is the gap? The gap is 131.56. Okay, so edit, move, relative 131.56. Okay, so that's the gap. So we have done this, but only thing is that 30 here has to reduce. So this will go plus 30. The last one we didn't change, right? So this will go 30. And this will go minus 30. Okay, so this is the end of the line effect. So now in essence we have the filter ready. Now an application engineer will tell you, oh, let's put these lines and then arbitrary spacing and then the arbitrary weights and then lambda by 4 and let them just run an optimizer. No, that's not the way to go about it. Okay, so let's go to M3, put the ground plane. Now the ground plane, I am going to put quarter wave. The quarter wave is 3480, 3487. 3487 or 500. That's okay. And the width is the same as this. And then I'm going to repeat this on the top like this. And then I'm just going to extend it to this. And this is my ground plane. So I have the structure of the filter ready. So now what I'm going to do is I'm going to put the ports. So we have port 1. Let's see what color port is that. U. Okay, doesn't matter. And this is port 2. Then you are going to have port 3, and then you are going to have port 4. Right, now let's make sure that the ports are on the right layer. So port 1 is going to be on M7, correct? And port 1 is on M7, port 3 is on M3, correct? Then the next thing is over here, port 1 is going to be, port 2 is going to be M7, and then port 3 is going to be M3, port 4 is going to be M3. So this is done, right? So our structure is ready. Am I going to do a momentum simulation? No, I'm going to do a FEM simulation. So I'll show you how to do that. Okay, first of all, go to create EM setup. In this EM setup, set the ports. So 3 is a ground reference for 1 and 4 is a ground reference for 2. Done. And then save it and go to EM setup back again. And everything looks okay, substrate is okay. Set the frequency plan to be going from 4 gigahertz to let's say 16 gigahertz. That will capture 9 to 11, which is our design band, right? And all generated frequencies, options, mesh, edge mesh, transmission line mesh, model, this. Now I'm ready to simulate. I can do a momentum simulation on this. You can look at a 3D EM preview of this. Okay, so this is a 3D EM preview of this, right? Sorry. So you are looking at the 3D EM preview of this filter, right? Bandpass filter. Now, I don't want to simulate it over here. I want to simulate in EM Pro. So one click of a button and it'll generate this filter, and it has some problem that it can't read the substrate. So I'm just going to delete the ports first. So once the ports are deleted, I'm going to put in a substrate. Okay, so I'm going to get a top view and then view all, and then I am going to insert. So I know the height from the bottom is going to be 309. So how do I get to this number 309? Well, if you look at the substrate in ADS, okay, so if you look at the substrate in ADS, you sum up from here, you are going to land up here. This is 291 plus 0.9 micron plus 9 micron. So you are going to have a 309, right? So that's the 309. and then I am going to do this and this, and then extrude it by 379 and just call it sub, and say done. Okay, so we have a substrate here, and this is our filter, right? So we have Ag or silver added already, we have copper added already. This is the resistive material. I'm going to delete that. And then we have got borosilicate. Borosilicate is 5.92, right? So I'm going to add this borosilicate to substrate. Okay, so what has happened? So we have it. So this is our filter. I need to put the ports, right? So to put the ports, I am going to go here and say new, no definition. And let me just zoom in somewhere on the edge and somewhere in the center. So it will automatically tell you where is the center. This is the center. And 283. So let's put one below the other. 283. Okay, so that's the port. And then this is port 1. And then it is a 50 ohm port. And extent is the sheet. And this is going to be the input port or the waveguide port. Right, so this is done. So port 1 is done. Next is port 2, which is over here, right? So let's just do this. So I need to add a port here, right? So I've said new, no definition. I will go and put the first point somewhere here, and second point it will give you the center. So that's the center, and 4993.16. 4993.16, right? So that's centered out. This is port 2, and this is going to be 50 ohm port, and extent I will set to 5276, 5276.16. So that's my waveguide port. So that's my second port done. So I am done with the entire layout of the 3D layout of the filter. I'm going to say file save project, and I will call this as BPF underscore X band, right? Save that. And once I have saved that, I am going to do the simulation. So this is adaptive. Let me add more points to it. Okay, 100. I'm going to accept the filter as is. I'm not going to do any alterations in it. So this is going to be first cut design. So if you want, you can change some things and try to tailor the response, right? But this is a first cut design based on formulas, and let's see if it comes close. That would be good enough, right? So I'm going to do a direct simulation, and rest is all set. Only mesh I will go and say after convergence use the finest mesh, and then this I'm going to say error is delta error is 0.1. So I'm ready with the simulation. I'll say create and queue simulation. So what I can do is I can put you on pause and come back later. Okay, the adaptive meshing at 16 gigahertz highest frequency with a delta error less than 0.01 is done here. Now it is doing the simulation at different frequencies. Now one thing I forgot is to save the fields. So I may have to run the simulation again with the field data, right? If you want to visualize the field, right? So for now, I am going to just leave this so that I can just see the S parameter response of the filter. And by the way, in this algorithm, okay, usually people refer to charts for computing the width and the spacing. While over here, I have the formulae to compute the width and the spacing based on even odd impedance pairs. So using even odd impedance pair, I use the same formula in the coupler design also, right? So the same formulas I'm using here. So there's no change here. Okay, we'll be done soon. It should be pretty close. See, the whole idea is your impedance inverters have to be right, or the capacitance between the two lines has to be right. So spacing has to be right. That's the first and the foremost thing. But then there are ways to tune it also. So looking at the response, you can do a tuning, not a blind tuning. So optimizer does a blind tuning. You don't rely on a blind tuning. You should have an idea of what is the uh, coupling capacitor. Should have some idea of coupling capacitor. So the optimization doesn't give you that idea, which this equation design will give you. Okay, I think it will be done soon. Okay, once it is done, I plot it. Then I'll run this again, putting you on pause so that I have the field data also. So let this finish. So why it is taking so many points? It is taking so many points because there are resonances here, right? Your G1, G2, G3, right? They were giving you resonators and then the coupling between resonators. So those resonances, right? So that's why it is putting so many points in this. So let's look at the results. Okay, so let's look at S parameters. So I'm putting on a rectangular chart first, and I will like to see S21 first. So at 9, we are pretty close. 9 and 11 is in the band. And then we have around 60 dB or 50 dB attenuation on the sides, right? So this looks okay. Let's look at S11. And the return loss is better than 10, right? So if you see here, the return loss is better than 10. And the filter, of course, there is this portion which you are seeing and this portion. So you are up to here, you are okay. So let's see. Uh, what is that? This is the horrible part in graphics, in that you ah come on, you can't change the point. Okay, so let me just read it out for you. Okay, at 9 gigahertz it is 1.25 dB insertion. At 11 gigahertz it's 1.25 dB. So you have a worst case 1.25 dB of insertion loss, and then you are having this response which is better than 10 dB. Return loss is better than 10 dB. Okay, S11, S22, they are better than 10 dB, right? So this is your filter response from the first cut design. This is a bandpass filter. So now I am going to just save it and I'm going to put you on pause. So this is acceptable. In many cases this is acceptable, right? Just that, you know, the end line effects are over here at 9 and 11. We are extending beyond 9 and 11, right? These are because of this. Let me show you. uh, okay, okay, let's look at the geometry. This is because of this. You remember we cut down 30 micrometer. It needs to be cut down more. The end effects are there, and that end effect is going to basically, if you do that, that is going to trim this portion. Response. uh, Again, I have to plot this again. Okay, so that's going to trim this 9 and 11 excess bandwidth here, right? If you have to adjust that, right? So that 11 megahertz side will come down, okay, by changing that overlap. and then this portion over here, right side, left side, will go up if you slightly change the what you call uh, the gap. Okay, so this is not very accurate, but this is for practical purposes, it's a good starting point. Okay, so now I have to put you on pause and look at field data. So okay, so I'm done with the same simulation, but now this time I am saving all the field data. Now let's look at some visualization, right? So I'll go to results, and this is the second simulation, and the S parameters are done. I am looking at, and are there surface currents, radiation efficiency, radiated power, VSWR, input power, field, surface fields. Let's try this one as we did for other simulations. And over here I am interested in band, which is 10 gigahertz, right? And I'm interested in, let's say, currents, so current densities, and I'm looking at copper, and I'm looking at silver, correct? And so this is our this, and I want to make it disappear. So I want to make this thing disappear. So let's go to transparency. Yeah, this is disappeared, isn't it? No, it is still there. Okay, now it has disappeared, right? Okay, so let's look at fine, and let's look at this one, properties, and I want to go to something like 100 amperes. Let's see, apply. No, not much. So let's say 10 amperes is a apply. Yeah, uh, let's say 20 amperes. Should have a full range, right? Okay, 15 ampere. 15 ampere. Apply. Okay, let me see if I'm recording this. Yeah, I'm recording. So that's being done. What I want to see is how the currents flow in these sections, right? So the blue one is the ground plane, right? And then these are the coupled sections, right? These are the coupled sections. So advanced auto and increment by, let's say, 2 degrees. Is that going to be very slow? And play. It's very slow. So what I'm going to do is I am going to stop this and increment by 4 degrees. How's that? And say play. Okay, so what you're looking at is this filter, and you're looking at, why is it going 90 degrees only? Okay, let's make it faster. This is too slow. 5 degrees. Okay, play. Okay, so this is what is happening to currents in ground plane and also the couple lines. Okay, so you can see what is happening to the couple lines, and this is multiple wavelengths long, right? Because if you see, just one section is lambda by 2, so these are multiple wavelengths long, right? So this is what's happening in a filter. So I'm not going to plot field. I'm going to stop here, right? Thanks a lot for this session. Thank you very much.